In this video we'll work another kinematics problem. We've got constant acceleration, which tells us that rotational kinematic equations are valid. So constant alpha implies rotational kinematic equations. Calculate the angular acceleration. This problem, I'm told that omega naught is 8 revolutions per second. Omega is 21 revolutions per second. And delta theta is 55 revolutions. Omega squared is omega naught squared plus 2 times the angular acceleration times the angular displacement. That means that alpha is the final angular speed squared minus the initial angular speed squared divided by 2 times the angular displacement. I was told that it was 21 revolutions per second squared minus initially 8 revolutions per second, which I'm squaring, divided by 2 times the angular displacement, 55 revolutions. When you plug all that in, that gives me 3.427 revolutions per second squared. Not in the normal rads per second squared, so we'll want to multiply that by 2 pi radians for 1 revolution. And when I do that, I get 21.5 radians per second squared. I'm then asked in part B to calculate the time required to complete 55 revolutions. Well, the final angular speed is equal to the initial angular speed plus the angular acceleration times time, one of the kinematic equations. Therefore, time is the final angular speed minus the initial angular speed divided by the angular acceleration. Now here's the case where it's actually convenient to have kept this alpha in revs per second squared, since my omegas are in revs per second. This is 21 revolutions per second minus 8 revolutions per second, and I'm going to divide this by 3.427 revolutions per second squared. The revolutions cancel. 1/2 cancels one of the seconds, the other one comes to the top. So when you put all that in, you get 3.79 seconds. A good practice making sure you understand the big board and how to get the kinematic equations, and being able to do dimensional analysis in order to be quick in working with units. That's all there is to that part of the problem. Now, in the next one, a breaker is thrown, causing the disk to undergo constant acceleration deceleration. If the disk has a radius of 0.5 meters and comes to rest in 10 seconds, what's the total distance traveled by a point on the rim as the disk decelerates? So we know right now it's going 21 revolutions per second. Okay? And they're only going to want to know, in this case, the 10 seconds that it goes to rest. T equal 10 seconds. Omega final, so this will be my new omega naught, new. Omega is going to be 0 revolutions per second. And they want to know delta theta is questioned because they want to know delta S. So I'm going to work with kinematics first. Delta theta is omega naught t plus 1/2 alpha t squared. But that won't help me because I don't have all the things that I need. For instance, I don't know alpha. Alright, but alpha is equal to omega minus omega naught over t. So delta theta is omega naught t plus 1/2 omega t over t squared minus 1/2 omega naught t squared over t. Delta theta, looking at this, I got a half an omega naught t here, and I had one, so that's 1/2 omega naught plus omega times t. Well, omega naught plus omega over 2 is omega average. The average speed times time gives you the displacement. I have everything I need here. I have 21 meters per second over 2 times the time, 10 seconds, will give me 105. Is that correct? 5 times 20, 105. That's in revolutions per second. 105 revolutions. Now I need to convert that to rads. So delta theta is 105 revolutions times 2 pi rad per 1 revolution. Put that together. You need a calculator, of course, to do this calculation. Come up with 659.7 radians. Delta S is R delta theta, so that's going to be 0.5 meters times 659.7 rad, and I get 330 approximately meters.